In number 1, it says a bullet of mass m is traveling horizontally with the speed of v naught when it hits a block of mass 100 m that is at rest on a horizontal frictionless table above. The surface of the table is a height h above the floor, and in this first scenario, scenario 1, the bullet and the block slide off the table and hit the floor at distance x from the edge of the table. So that means that they the bullet goes into the block and they together move, like it's drawn right here. In scenario 2, the bullet instead passes through the block instead of remaining in it. In which scenario will the block land a greater distance x from the table? Justify your answer with a paragraph length response. Equations, we're allowed to have equations, but if they're not enough by themselves, you would have to explain the equations. Okay, so for this one, first of all, just like which block lands farther away? Well, the one that lands farther away is the one that's moving fastest. So that's our first step, is saying, okay, the farther away is just the fastest one. And now we need to figure out which one is faster. So I redrew the diagram just so you guys can see a better idea of it. Right here, my before is a bullet coming in, and then they stick together. Obviously, when they stick together, it's going slower than the v naught because you just gained 100 times more mass. But if they're stuck together, then they would both be moving to the right. Now, the second scenario is it's still coming in, same mass m with the v naught or velocity of v naught, but now instead of sticking together, the bullet passes through. So it passes through like this and is continuing on. If the bullet passes through the block, that means the bullet is going faster than the block is here. Now what we want to compare is in which situation does the block end up going faster. So if we think about, momentum has to be conserved. They're both starting with the exact same momentum. Here, that momentum is, well, in either case, they're shared between the block and the bullet. But in this case, they both move at the same velocity. In this case, the bullet is going faster than the block, meaning that in this one, the bullet has more momentum than the bullet does here. So here, this is going faster than in scenario 1. Because it passes through the bullet, it doesn't stay with it. So then if this one is going faster in scenario 1, then this one must be going slower than in scenario 1, because momentum is still conserved, right? That means if this one is going faster, it has more momentum than here, but it still has the same total momentum, so the block must have less momentum compared to scenario 1. So then our paragraph length response, my paragraph length response is I said that that the block in scenario 1 lands a greater distance, x, from the table because the block in scenario 2 goes faster, in scenario 1 goes faster after its collision with the bullet. You probably don't need to write all of this. You could just say the block in 1 goes farther because it is moving faster. And now we need to explain how we know it's moving faster. If you want to be super detailed, we know that farther is faster because your delta x is just velocity times time. So a greater velocity means a greater displacement or greater delta x. But I think it's definitely enough to say that the going farther because it goes faster. If you really wanted to, this is just extra, making sure you really hammer home that point. And now we need to explain how we know that the block in scenario 1 is going faster. So, which is this explanation that we just talked about. In the scenario 2, the bullet passes through the block, which means that the bullet is going faster than the block, which means that the block must be going slower than it was before. So my explanation says that in scenario 1, the block and the bullet move together with the same velocity. In scenario 2, the bullet passes through the block, meaning the bullet goes faster than the block. So, because in this case where the bullet goes faster than the block compared to when it's stuck with the block, here the bullet is moving faster. So, the bullet is faster, which also means more momentum in scenario 2 than in 1. If the bullet is going faster in scenario 2, well, momentum still has to be conserved, so that means that the block must be going slower in scenario 2 compared to scenario 1. So since the total momentum of the block and bullet must be conserved, the block must have less velocity, or therefore less momentum, in scenario 2 than 1. And if you wanted to like draw your little diagram on here, that's fine, as long as like you can't just draw this, you can't just like do this and write faster and slower, you have to write out your explanation. So again, what we said is when they're compared to when they go together, in scenario 2, if the bullet goes through the block, then it must be going faster than the block, so it must be going faster than the bullet here. If this one is going faster than the bullet here, then the block must be going slower than the block here, which is what we said. The block in scenario 1 would be going faster. So, and if this one we said that scenario 2 is going slower, so you could then say, therefore, the block in scenario 1 moves faster. Or you could say it with a greater speed, all meaning the same thing. Okay, number 2, a block of mass M slides down a frictionless slide. The block is released from rest at the top of the slide H and collides inelastically with a block of mass 3m at the bottom. The two stick together. Determine the velocity of the box immediately after their collision. So first we have m, and we need to know what velocity it comes in with, and it's going to hit 3.5 m, and then they're going to stick together, and then what I'm actually looking for is like this right here, this stuck together velocity. But first I need to know the velocity m comes down with. So we're going to use conservation of energy. Up here I have potential energy. It says it's released from rest, so kinetic is 0. Then when it reaches the bottom, your potential is going to be 0, so you have only kinetic. So that means that all this potential is going into kinetic energy. So mgh equals 1/2 mv squared. The mass cancels out, so it doesn't matter if this was a bigger mass, it would still come down with the same velocity. And then multiply your 2 up, so 2gh equals v squared, so the velocity it comes down with is square root of 2gh. So this is coming in with 2gh. Now if this one comes in, hits this one at rest, and they stick together, now I'm looking for this final velocity of the two together. Well, momentum is conserved, so momentum before has to equal momentum after. Before this one's at rest, so it's just this mass times velocity, which looks weird, but it's okay, because our velocity is square root of 2gh. And then that is going to go into m moving at some velocity v plus 3.5 m moving at some velocity v. That just becomes 4.5 m velocity v, m square root of 2gh. You'll notice that the m's cancel out, and to get this velocity after this v that we're looking for, we divide by 4.5. So nasty looking answer, it's okay. It is this square root of 2gh divided by 4.5, which makes sense because the velocity you're coming in with is now shared between a total mass of 4.5. Okay, cool. Again, in this case, your mass is canceled out here, so if this had been a much bigger mass, it still would have come down with the same velocity, but if it had been a much bigger mass, it would have come down with more momentum, which would have changed this velocity. So, just point that out. Number 3, 2 small uniform balls of identical density and size. That means that they're the same mass. They're the same mass, because if they have the same density and same size, they're the same mass, are fired from a toy gun towards a wooden block. A is highly elastic and bounces backwards, so I'm going to draw A is going to come in and then come back out. This is situation A. And then in B, the ball is still going to come in, same mass, same velocity, but instead of bouncing off, it's going to stick to the wood, and then you can assume that these two together would then go off at a slower velocity than before. Which ball transfers more momentum to the block? So think about when this comes in and bounces off, obviously this one's going to go like to the right as well, because when this one transfers, it hits with some force, it transfers momentum to this block, and then obviously this one coming in and sticking to it transfers some of its momentum to the block as well. I'm asking in which case or which ball transfers more momentum to the block. Well, the way I thought about it is however much momentum that the block gains is how much momentum this one changed by. So they have the same, or I'll just write the change in momentum of the block is just the change in momentum of the ball because momentum is conserved. Remember, momentum being conserved doesn't mean the individuals can't change. They totally can. It's just that the total can't. So if this one loses 5 units of momentum, that means the block gained 5 units of momentum, etc. So now our question is, in which case, ball A or ball B, did the ball have the greatest change in momentum? And the answer is A. A has a greater change in momentum because it doesn't just like stop. It stops and turns around and goes the other way. That is a much bigger change in velocity because it slows and then turns around and reverses direction, whereas this one just slows down. So block A or ball A has a greater change in momentum because its velocity stops and then reverses direction, whereas ball B only slows down its velocity. It loses some of its velocity, but it's still going to continue going to the right. That's not a big change. Coming in, turning around, and going the other way, that is a much bigger change. If you want to think about it in terms of the math, if ball A was mass coming in with some velocity, if it were to turn around and go back the other velocity, it doesn't say it comes back with the same velocity, but let's say it did, then your change in momentum here would be m, change in velocity. You do velocity is final minus initial. This would be in the opposite direction, which is negative. So you would have m negative v minus v, which is negative 2mv. Which is very definitely a lot more change than if I just came in with a velocity v and stopped. If that was the case, then your change in momentum here would just be mv, or negative mv, because it's losing. So that's the numbers. I wouldn't put that in your explanation, but that's another way to think about it. Number 4, a block of mass m comes with the velocity v naught towards another ball of mass m that's initially at rest. They collide elastically, so when they collide elastically, that's those like crazy where momentum is conserved and kinetic energy, but there's a special case for equal masses. When equal masses collide elastically, what happens is they just switch velocities. So instead of this coming in at v naught and this one being at rest, now this one is at rest, and this one is going up with v naught. And how high does it reach? Well, if it's coming in with a velocity of v naught, this is all kinetic energy. When it goes up to the very, very top, at the very, very top before it falls back down, now it's all potential energy. So that's kinetic going into potential, so 1/2 m v naught squared, because that's the initial velocity, because this one transferred all of its momentum here and now is at rest, equals mgh. M's cancel. We're looking for the height, so we've got v naught squared over 2g. When you divide the g over, that would be your height. Number 5, in both situations, the first block comes in with a velocity v and collides and sticks to the second block. I didn't say this, but they are at rest, sorry. Both of these are at rest. And we want to know in which system when these two stick together, so like the M and the 3.5 M, and the 2M and the 3.5 M, in which situation is the system moving faster. So how I thought about it is just the momentum it's coming in with. So this one is coming in with a momentum of mv, whereas this one's coming in with a momentum of 2mv. So even though they're coming in at the same velocity, because this one has twice the mass, it has twice the momentum. So yes, there is still a little bit more mass in total that it's sharing between, but it still came in with more momentum, so it has more momentum in the end, so it'll go faster. So I said this one is going to be the faster because it starts with more momentum in the system. Now, if you have time, you can always double check your answer and do like the calculation. So here, mv equals mx plus 3.5 mx. The m's cancel out, so v is just 4.5x. So then divide the 4.5 over. So then your x is 1 over 4.5v. Here you've got 2mv is equal to 2mx plus 3.5mx. M's cancel out again. 2v is equal to, this is 5.5x. So divide the 5.5 over. Now these are not like nice numbers, so I just put it in a decimal point so I could see the comparison. So that is 0.11v, and then this one is 0.36v. So this is going to be faster than this one. Obviously slower than the incoming velocity because it just picked up more mass, so it's sharing its momentum over more, so it has less velocity. But this one is a greater velocity than in this situation. But you don't have to do this. You could just say this one is coming in with more momentum, total momentum at first, so then the whole system will go faster when they stick together. Cart of mass m is released from rest at a height of h, and I want to know what the velocity at point P is. So here, if it's released from rest, kinetic energy is 0, it's all potential. Here it has both potential and it has kinetic. So my mgh is going to go into 1/2 mv squared, plus I also have another potential, or I still have potential energy. My height is 2 radiuses because the full diameter makes up 2 radiuses. 2r. M's cancel out. I can subtract this over. So you have gh minus 2gr equals 1/2 v squared. Multiply everything by 2 equals v squared, and then your square root of 2gh minus 4gr. Another cart of mass m is waiting stationary at the bottom of the roller coaster. The two carts collide elastically. So this is saying, I'm going to redraw it. This one is coming in, and then we'll hit this one right here who's just waiting to be hit. So in order to find what the velocity after is, first of all I need to know what velocity it's coming down with. Don't make the mistake of using this. This is the velocity right here, not what where it's like coming out, right? It's coming out on the ground. So we're going to find this velocity right here. At this point, it's all kinetic energy, and it came from all potential up here. So you can just do mgh will go into 1/2 mv squared. And then 2gh is your v squared, so your velocity at this point is square root of 2gh. So that's saying at the bottom, m comes in with square root of 2gh and hits another m. The two collide elastically. Well, elastic, when they're equal masses, is a specific or special case where then they just switch velocity. So now this one is at rest, and the second mass is going to go off at square root of 2gh. So what is the velocity of the second cart? Is just square root of 2gh, because it just switches velocities with this one. So basically, if they're equal masses and one's at rest, and you want the velocity of the second one after, it's just the first velocity. So they have to be equal masses, and it has to be colliding elastically. And then lastly, frictionless roller coaster of mass m starts off at point A with a speed. So here you have both potential and you have kinetic energy. And I want to know how high up on the last loop, this is not a loop, but on the last hill, you are able to reach before it stops. So I want to know how high I can get, and it's going to be greater than h, because at the very, very top before I stop, it's going to be all potential energy. This point I had both potential and kinetic, so I can go even higher to where it's all potential. So then you start plugging in, mgh plus 1/2 mv naught squared is going to go into all height. Don't call it h because we are already using h as a given, so let's call it x, or like h at the top, I don't know, whatever you want to call it. M's cancel out. Wow, this is really easy. So then you just divide g over. You can just leave it as gh plus 1/2 v naught squared over g, or simplify this a tiny bit. These g's cancel out, leaving you with just h, but it doesn't cancel out here, so I would have v naught squared over 2g is my x, or my height. And this is, the x is the very, very highest point it can go up. Okay. Study hard.